great pleasure to introduce Dr. Paul Baker. Dr. Baker was a professor in Pittsburgh until 2010. And then he said, oh, let's have some more fun. We're joining SCIEX and being a strategic senior scientist at SCIEX ever since, with a stint at Avanti Polar Lipids in 2018, and some sabbatical also. So we know Paul Baker for a long time as one of the leading figures and thinkers behind the scene. So therefore it's my great pleasure to welcome you today to our Holy Halls and talking about electron activated dissociation. Now, you may know that we have a paper on EAD. The author of that paper currently is in qualifying exam. So has to defend the idea of EAD in front of Carlito Ribrilla and other people on campus. So we wish him good luck, telling them that EAD is here to stay. Okay, Paul Baker.
Thanks, Oliver. I appreciate it. So thank you for the kind invitation to come speak, and obviously for the introduction. Yeah, I mean, the move from academia to a vendor was a difficult one, but I had gotten I happened to go through the ranks as a junior scientist during a time when funding was just about as bad as it could ever get. And I got a 6th percentile on an RO1 in heart, lung, blood, and they funded up to 3%. And
wow.
They told him, the dean kindly says, oh, well, here's 6 months bridge funding for you or 6 weeks bridge of funding to get your next grant. And so they were showing me the door, and it turns out SCIEX has been a really great place to land. I've actually been able to do a lot of things there that I don't know if I'd ever be able to do had I stayed in academia. So yeah, I want to talk today about a project that I've been working on the electron activated dissociation is something that I found in the Black Labs of Toronto when I was wandering around at night. Met a guy by the name of Takashi Baba, and Takashi is the one who invented this EAD cell, and we started a collaboration about 6 or 7 years ago, and a lot of the papers that are out there on lipids were done with Takashi and I working, basically doing things outside the rules and working late at night when to try and show the power of what electron-based fragmentation can do. So kind of an overview of what I want to talk about today, the challenges. I think it's really important to set the context, and obviously this is a very savvy group here, so I apologize if I'm going to be redundant with you, but I think it's really important to understand what are the inherent challenges that we're going to face in studying lipidomics. And briefly talk about targeted lipidomic analysis, then head on to the Xenotoph 7600 with EAD, how we can structurally characterize lipids with EAD, and then talk about high resolution targeted metabolomics with the Xenotoph. So the field of lipidomics, as I consider it to be, the real kind of the modern era, really started in the 80s with Richard Gross at Washington University in St. Louis, coining the term shotgun lipidomics, where infusion-based or flow injection-based analysis, where we're going to be able to identify lipids by class by looking for common precursor ions or neutral losses. So for PC, for example, if you have a molecule undergo collision-induced dissociation and it generates a fragment of 184, it'll be collected into your data set and it'll show you PC. But it also could be sphingomyelin, which is something that we'll discuss a little bit later. But it's really evolved quite slowly up until, I think, really in the year 2000, 2002, I think it was, when the glue grant Ed Dennis got for the Lipid Maps Consortium. And they had various roles, but I think one of the most important or biggest impacts that they had on the lipid field was this classification system. It was an attempt in the early days to try and unify and harmonize, standardize lipidomics. There's a lot of different names for the same compound. It was kind of the Wild West, and so they brought together some of the big minds in lipidomics to try and add some standardization to here. And so they broke the lipidome up into about 8 different categories. All told, it's estimated that the number of individual lipid molecular species is about 150,000. I won't defend that, but I think that's Ed Dennis and I were talking. We thought that seemed like a reasonable number. Could be more, could be less. It's interesting because most people say, well, I've got a lipid panel, I'm looking at 700 compounds. And I have some, I think we're going to go deeper into that in the next couple of slides to really understand that even if you think you have a single entity, you probably don't. You probably have a group of molecules, and they all add up to be the 150,000. So I like to envision the lipidome as like an onion. All right, we got our little picture of an onion here. And as you look at a lipid, you can start peeling the layers and getting deeper and deeper into the structural specificity of that compound. So at the very outside of the lipid, maybe we're looking at lipid class, all right? PE for phosphoethanolamine, sphingomyelin, or triacylglycerol. Technologies that can be used are thin layer chromatography, flash chromatography, NMR. In the 1960s, there were books published about the lipid composition of food, and I would say it was 20% PC, 16% PE. It was at the class level, all right? And so that's that outer level of that, or outer layer of that onion. The next layer is what's called the sum composition layer, all right? So in sum composition, we have, let's see if this works. Does it work? Yeah, it does. We have the nomenclature is denoted as such. We have our class here, PE for phosphoethanolamine. The next number, 36, is the total number of carbons among the fatty acids that are attached to the glycerol backbone, and this colon-1 refers to the number of double bonds. What we don't know is what fatty acids are combining to create that 36-1. All right, we just know that it's PE. So really all the information we have is at the class level here, and maybe some inkling of an idea of what's going on at the fatty acid level just based on this number here. And this is, you know, the results that were generated with shotgun lipidomics and discovery experiments, untargeted experiments. They're going to quantitate, the majority of them quantitate at the sum composition level. But you can imagine from a metabolic perspective, not knowing the fatty acids that are playing there is really limiting in understanding what is going on biochemically, right? So the next layer would be for us to identify at the fatty acid level. So rather than 36-1, we're saying it's 16-0 or palmitic acid and 20-1, or stearic acid and oleic acid. By convention, the Lipid Maps Consortium says if you don't know if it's at the SN1 or SN2 position, you use this underscore. Otherwise, you use a slash when you know it's at the 1 or 2 position. So we don't know the position, but we now know the players. And this is where we're at with our targeted method that I've worked on for the last 6 or 7 years. It seems to be pretty widely adopted. It's a helix-based method. Separates by class. We do that to try and avoid isobaric interference among different classes. There's an infusion method that can be done on the 6600 that you guys have, MSMSL, or even the untargeted or discovery experiments. Just note that, yes, you can identify at this level, but you're not going to quantitate, because by definition, a good discovery experiment is going to give you 1 or 2 really nice MSMS spectra per compound. You don't want to waste time taking too many MSMS spectra because you'll miss compounds. And as a result, you really don't have anything to integrate. So the integration or the quantitation is going to happen at this level, but you can identify with discovery experiments, at least the players. And there's kind of like a theoretical line here, kind of an imaginary line. Once we start getting down into the deeper layers of that onion, into the lipidome, so the more esoteric aspects of the structural nature of these molecules. For example, fatty acid position. 16-0 in this particular case, the palmitic acid is denoted as being located at the SN1 position, and the 20-1 at the 2 position. I spent quite a bit of time a number of years ago using differential ion mobility to be a way in which we could identify SN1 versus SN2. But the tried and true method is phospholipase A2 hydrolysis. You take your molecule, you measure it by mass spec to MSMS, you find 2 fatty acids. You take that same molecule, you digest with PLA2, you run it again, you find out which fatty acids disappeared, and that would be the fatty acid at SN2 position. That's the tried and true gold star method. But it turns out that EAD is actually a method that can work pretty well to determine that. Double bond position. This turns out to be really important lately. I was at the SLING conference, Marcus Wank's SLING conference in Singapore this year, and really one of the better lipid conferences globally. And I would say 70 to 80% of the content was around strategies people have devised to determine the location of the double bond. And why is that important? Because that's the basis of biology. I mean, there's enzymes at work that need to have a double bond in a specific position in order for them to function. So understanding the structure of the lipid at a level of this depth is actually pretty challenging. We got Stephen Blanksby's idea, ozone ID. You drill a hole in your instrument and you pump ozone in there and you look at fragments. The Paterno-Bucchi reaction, or HVPD, and it turns out now with EAD as well. And then the final one is the stereochemistry of that double bond located here, at least in this example, at the delta 11 carbon. And how do we determine cis or trans? And there's really, I don't know, a very good way to take an intact molecule and determine the stereochemistry. High resolution NMR, some complex LCMS strategies. But really up until now, this is kind of where the edge of, from what I can tell in the current field of lipidomics, this is the edge of where people are at, trying to figure out the double bond position. And it turns out that EAD fragmentation can actually give us all of this information in a single experiment on the time frame of about 25 to 35 milliseconds. All right, so it's amenable to an LC time frame. And a lot of the data I'm going to show you was done with some standards, but also a lot of the data was done with plasma in more discovery type experiments. So this is a thought experiment that I like to show off because I brought up the idea of some composition level. And what does it mean when you see that? And the vast majority of the literature in lipidomics are referring to lipids in this term, right? So what does it mean? And so if here we have on the bottom of the slide, we have basically the number of possibilities this could refer to. So well, at least what do we know at this point? If we have PE36.1, well, we've got this entity, PE36.1. But what if we go down to the fatty acid level? And if we do that, considering fatty acids that are typical for mammalian biology, we could now increase that number of possibilities to 5. If we're looking at the positional isomer level rather than and determining 14O at the SN1 or the SN2 position, now we have 10 compounds, right? Go to the next level where we're considering fatty acids that are likely in mammalian biology. So for example, this is myrstolaic acid, the 14-1. We could have a double bond at the delta 8, delta 9, or the delta 11 carbon. They're different fatty acids. They have different biology, different metabolic outcomes. And now all of a sudden we've increased that number to 28. And are they cis or trans? Boom, we could have 56. All right. Now, is it likely that we have all 56 in vivo? Probably not. But what the idea here is to show you that when you read something in the literature of some composition of P36.1, you got to ask yourself, what does it mean? And you can't use the word biomarker when you're talking about PE36.1. And in fact, about 6, 7, 8 years ago, I can't remember quite which, there was a paper in the New England Journal of Medicine where they had identified a biomarker for Alzheimer's disease. And it was PC368 or 38.6. They hadn't even done MSMS on the compound. They didn't even know that it likely had 22.6. Makes sense that docosahexaenoic acid would be involved in neuronal development. But, this was something that had, exposure on New York Times and NPR. And they were talking about this some composition where they really had not dug down to what is going on biologically, in my opinion. So just kind of put it all into context, the complexity as well as the challenges we face when we're trying to do lipidomics. So one way that I thought to address some of the issues in lipidomics, one being the extensive isobaric interference among different lipid classes. So it turns out, like if you look at phosphatidylethynolamine or phosphatidylethylamine or phosphatidylethylamine, there are many compounds within each of those classes that have the same precursor mass and also share one or more fragments. So as a consequence, that's one of the challenges with software interpretation of discovery lipidomic experiments, because it'll say mathematically they'll all fit, and unless you've got really good retention times or consistency, the software usually likes to say they're all there. So what I found is with the software, usually there's a lot more false positives than you would get if you were to really dig in deep and manually address it. But in this particular case, we're using a Luna amino column. It's a helic-like. It's not a true helic column, but it does separate very clearly, closely to normal phase. So you can see all of our polar lipids being separated nicely, but has just enough hydrophobic character that it can separate out the ceramides from the monoacylglycerols from the diacylglycerols. It does a nice job in terms of almost giving you a screen, 17-minute screen of 2,250 molecules. It's actually around 2,500 molecules now, over 21 lipid classes. This is just another way to view the data, showing you from the targeted effect. On the y-axis, we have our Q1 mass, and on the x-axis, we have time. This is positive ion mode up top and negative ion mode on the bottom. And again, you're seeing just a little bit of spread in time within each class. So it's not all of the molecules coming out simultaneously. We actually have about a minute as those elute. But clearly, we're separating the PC from the PE from the PS, one of the major 3 groups that we need to make sure are clearly separated in order to avoid the isobaric interference. The data that I showed you was done on a 7500. That is our flagship triple quad instrument. The previous instrument, the 65 Plus, was also a very sensitive instrument, But as you can see, the dynamic range, because we have that increased sensitivity, in particular in the negative ion mode on the 7500, we've increased the dynamic range of that targeted assay to cover almost 5 orders of magnitude linear dynamic range. Unfortunately for all of us here, there's about 12 orders of magnitude linear dynamic range on the lipidome, but every little bit counts as you're trying to improve your coverage. So before I move on to discussing accurate mass and EAD, just kind of an overview of where I think the field is. And I've noticed this over the last 3-4 years. There has been an absolute move and trend in the lipidomics field towards more targeted analysis first, and then using that information to direct untargeted efforts. And the reason for that is, as I mentioned before, the fact that you're getting so many false positives that you don't have confidence in the data that are being generated by the software is really turning a lot of people off. And so wouldn't it be better in a lot of people's minds, let's take a broad net, which is what this method is. Take a broad net, cast it out there, see what you can see, like, hey, something's going on with the triglycerides and the sphingomyelins. And then you can do sample prep. You can figure out ways in which, like, I want to figure out everything there is to know about the sphingomyelins or the triglycerol class. And what I'm finding in my own experience, if you can minimize the noise, if you can minimize the stuff that's not important, you have a much better chance of success when you're looking for the things that are important. But again, this method is only going down to the fatty acid level. So I can tell you that I have a PC molecule that has palmitic acid and oleic acid, but I can't tell you much more than that. So what if you want to, delve deeper into the lipidome, and that's where the Xenotoph is really poised to help us out. So this is the outside of the instrument. It's a bench top. It's about half the size of the 6600 that you have in your lab. It no longer has to sit on the floor. It is an N-wave TOF, so essentially if you're looking at the inside here, our ions are pushed here with the accelerator. They hit a reflector, they go back down, another reflector, and they hit the detector. So it has a path length that allows for resolution of around 35 to 45,000. And I think it's safe to say, although I was talking to Laura and he corrected me, but I think it's to say in the traditional QTOF platform, there hasn't been a whole lot of advances in the last 10, 15 years. I'd say within the last 3 or 4 years, there have been some advances in QTOF, but there's always been a kind of a bias, especially in the small molecule world, against QTOFs because they haven't been sensitive enough, most likely. So I want to talk about an advance that we've put into the 7600 that really does address at least the sensitivity issue on there, and it's called the Xenotrap. All right, so what you're looking at here is a schematic or a cartoon of the inside of a mass spec. This is the TOF accelerator. The TOF chamber obviously is going through the ceiling. Right here is Q2, and what we've got inside of Q2 are fragments that were made. We have Q1 here. We've isolated a precursor. We've blown it up at the beginning of Q2, and now we have our fragments sitting in Q2. All right. And the thing to note here is, and an explanation as to why QTOFs have been traditionally insensitive is because they are continuous ion beam. All right, so ions are continuously entering the mass spectrometer. They're being blown up, and they're being pushed to the top accelerator. But at some point, we have to shut the gate here. We have to close the door and push those ions up through the time of flight chamber and let them hit the detector. While that door is shut, those ions are just going to vacuum. All right, so we're losing. The idea is called, or the concept is called duty cycle. Duty cycle is defined as the percentage of ions that enter the mass spec that actually hit the detector. And traditional QTOFs, it's only about 5 to 20% of the ions that enter the mass spec actually hit the detector. So, and there's another aspect of traditional QTOFs that's also challenging, especially in particular for lipidomics and metabolomics. So we have our example here in Q2. We have our large fragment. So this is populated with fragments. All right, we isolated Q1, we blew them apart, and we have small fragments depicted by the white dots, and we have large fragments depicted by the black dots, and everything in between. In order to get these fragments into the accelerator, there is a uniform electrical field that's pushing those fragments towards the accelerator. But if you can imagine, if you have a uniform electrical field, molecules of different molecular weights are going to experience different motive forces. So what happens if when I activate the animation here, watch the differences that are occurring among that distribution of fragments. Notice how the small fragments shoot through and they actually overshoot the accelerator. And the larger fragments, not all of them get there. So what happens is we have a bias towards the fragments that are being collected in the accelerator. So when I actually push those fragments, it's not homogeneous. In fact, if we imagine a Cartesian coordinate system with molecular weight or intensity, on the y-axis and molecular weight on the x-axis, we have almost a Gaussian distribution where there's a bias towards the mid-molecular weight range. And in fact, we have a distinct bias against lower molecular weight fragments. And that's really what we need for lipidomics and metabolomics. We want to be able to measure those fragments at 75 Dalton or 50 Dalton. And so because a commercial mass spectrometer is a compromise, they basically said, well, most peptides are around 700, so that's what they made the algorithm to push those fragments into the TOF accelerator, and it's going to favor the mid-molecular weight range, around 700 to 800 Dalton, right? So when they created the XenoTOF, they wanted to address both issues, sensitivity as well as that mass bias. So essentially we have the same thing here. We have Q2, we have our TOF accelerator, but instead of just allowing that to be a continuous ion beam, we're actually going to add gates, basically ion trap, in the end of Q2. So what happens now is that once we have isolation in Q1, we blow up our molecule, now we're going to catch all of the fragments, right? And the beautiful thing about a trap is, one, is that they scan very quickly, but two, they scan in a molecular dependent manner. So they figured out an algorithm to allow that the high molecular weight ions leave first, the low molecular weight fragments leave last. They all arrive at the exact same spot, and they go through the time of flight chamber. So the cool thing there is that we no longer have that bias towards the mid-molecular weight mass. So now we have a detector that is, or a mass spectrometer that's also going to be equally good for the small fragments and the large fragments as the medium molecular weight fragments. The other thing that's happening is that while those ions are flying through the time of flight chamber, which takes about 600 to 700 microseconds, the fragments from the previous collision are filling up right here. So what's happening is, instead of those ions going to vacuum, we're trapping them, and we're saving them up to throw them to the time of flight chamber in the future. So in the end, what happens is that we improve that duty cycle to about 90 to 95%. Now 90 to 95% of the ions that enter the mass spec actually hit the detector. If we're looking around the peptide mass range, 700, 800 Dalton, we're looking at about a 10x increase in sensitivity. If we're looking down in the lipidomic or metabolomic molecular weights for fragments, we're looking at about a 10 to 20, 10, 20, even 30-fold increase in sensitivity. And that's because we no longer have that mass bias towards the mid-molecular weight range. Just point out the detector. It's fast, 130 megahertz, or 130 hertz, which means that we can do 130 MSMS per second. Most of our high-end triple quads are around 200, 250, so it's close. Has a large linear dynamic range, 5 orders of magnitude. And what it turns out is that this instrument, in our experience, has the same sensitivity, roughly the same sensitivity as our 6500 plus. In some cases, it has the same sensitivity as our 7500 triple quad. So this has the quantitative power, the sensitivity of a triple quad, but you're still getting accurate mass. So the final thing I want to talk about, and it's really going to be the theme of the rest of the talk, is the EAD cell. I know that's what you guys are here to talk about. What is the EAD cell? Electron activated dissociation. It is a cell that is designed to allow us to vary the kinetic energy of the electrons. So some of you may be familiar with ETD or ECD or hot ECD. These are methods typically used for peptides. And the reason for that is that at these kinetic energy value levels, you require a multiply charged target, typically a peptide that would be multiply charged in the positive ion mode. But because we have a tunable voltage or kinetic energy, we found that if you go to levels above 10, we're in this range called EIEIO, or electron impact excitation of ions from organics, where we can actually break apart a molecule that is singly charged. This opens the door to metabolomics and lipidomics for electron-based fragmentation. You really can't do it with ECD or even hot ECD. But when we get to levels of a 10 to 15 electron volts, we now can actually fragment molecules in the positive ion mode. And the way it works, this is the axis, or the mass axis of the instrument. All right. On either side, we have an ion trap or ion gate, so that we can trap our ions in the center of our trap. On the either side, these black knobs are covering electron filaments. So that's going to be our electron source. They alternate to increase the lifespan of the electron filaments. And then on the top and the bottom, we have two 1 Tesla magnets that are creating a magnetic field to trap the electrons and the ions in the same space. And you can keep these gates shut for as long as a second. So anywhere from 5 milliseconds to an entire second of reaction time to break down your compounds. Then once the reaction is done, you open up the gate, it goes through Q2, goes to the accelerator, and we detect with the TOF. So what's the big deal about electron-based fragmentation? So CID fragmentation, which is the basis for most of the mass specs probably in your lab today, is a thermal fragmentation method. It's a soft fragmentation. And I liken it to a pyramid. All right, so the pyramid is created of all the different bond energies. At the very top, we're going to have the weakest bond energies, and at the bottom, we have the strongest ones, like the carbon-carbon bonds, the carbon-nitrogen bonds, the carbon-hydrogen bonds. And with CID, you have a finite amount of energy associated with the collision. You've got your ion, you hit nitrogen, it breaks apart. And there's an amount of energy that is associated with that impact, right? And so you're going to start chipping away at the top of that pyramid. And all of a sudden, you start dissolving that pyramid. But at some point, you run out of energy, and you've got your pyramid without a top. But you have not been able to break those really strong bonds there at the bottom of the pyramid. That's CID. The most labile bonds are going to break first. I think of EAD, it's a complementary fragmentation method, but I liken it to more like a sniper rifle. All bonds are equal. All bonds are equally susceptible to breaking with electron-based fragmentation. So you no longer have this hierarchy of bond strengths. You can break carbon-hydrogen bonds, carbon-carbon bonds, ring structures. They're all equally likely to break. And what that does is allows us to break a molecule in unique ways. It generates significantly more fragments. And those fragments then can be used for structural diagnosis. So how can we use EAD to characterize lipids? So from CID, we know that we can kick off typically on a lipid, let's say, for example, phosphatidylcholine. We can subject that to CID. We're going to kick off the two fatty acids, and we're going to kick off the head group. That's pretty much the limit of what we're going to be doing with CID. Those are the labile bonds. They're the ones that are most easily broken. And we find that with EAD, we can do the exact same thing. We can kick off that head group, and generate a diagnostic fragment for each head group. Noted for CID-based shotgun lipidomics, there's about 8 to 9 common fragments. Turns out there's a lot more. You can even do the galactosylceramides, the MGDGs, the DGGDs, glucosyl versus galactosyl DGs. There's diagnostic fragments that we can use now to identify those as a class. But just like we showed before, that's really not going to give us enough information. That could give us some composition, but let's dig in deeper. I want to understand about the fatty acids as well. A point I'll make here is that the data I'm presenting was all done in the positive ion mode. And as you can imagine, it's going to be a more efficient fragmentation in the positive ion mode because we have an electron, which is negatively charged, hitting a positively charged molecule. All right? So that's going to be a more efficient. So if the lipid is anionic, we're looking for the sodium adduct, potentially the disodiated adduct, or even the potassium adduct. Now, that being said, it is possible to do negative ion mode fragmentation. It's not very efficient. So currently, the 7600, the kinetic energy of the 7600 is throttled at 25 electron volts. So if any of you recall doing GC, where you have the old EI days, that's usually around 80 electron volts. So I will say this, that currently, because of the low kinetic energy in the negative ion mode, you have to really let the molecule sit for a long time. They have to react a long time in that trap, in the EAD cell. I will say this, that it is simply a firmware thing, and that they're working right now. I know that some of the instruments up in Toronto have been unleashed. There's a paper pending right now about this. And so it can go up to 70 electron volts, and they're starting to get EI-like fragmentation. And I think it's amazing to think about that, because there are literally hundreds of thousands of EI spectra that have been annotated with GC that we'll have access to on an LCMS system, which would be pretty exciting to see that happen. What about the backbone? Remember I said PC, if you do a shotgun experiment and you're looking for fragment molecules, precursors are 184. Most people say, well, that's PC, but it could also be sphingomyelin. In fact, a lot of people spend a lot of time trying to distinguish between sphingomyelin and PC. Turns out with EAD, it's very simple. In sphingomyelin, EAD is going to fragment this dotted line right here. It's going to fragment along the sphingosine base, and it's going to generate a singlet at 225 every time. Phosphatidylcholine is going to generate a doublet at 224 and 226 every time. One cool thing about this is that you don't have to tweak the kinetic energy, you don't have to tweak the ion intensity or the electron intensity. The only thing you want to do is probably go around 20 to 30 milliseconds. That's it. This is not one of those, this is not a set of parameters you have to really tweak to get the best information per molecule. It seems pretty generic settings. So again, this was done on an LC time frame to get this data. So what about the fatty acid characterization? So regioisomerism. What's at the SN1? What's at the SN2? Why do we care? Well, the phospholipases A2, which are activated during inflammation, they act at the SN2 position, and those fatty acids then can be converted into pro-resolving or pro-inflammatory lipid mediators. All right. So understanding what the players are important for biology. So what's at the SN1, SN2? Turns out that the electron or CID-based fragmentation is going to fragment right here. All right. And what that does is it's going to release an intact fatty acid. So if you're in the negative ion mode and you're looking for 16O or palmitic acid, it's going to release a 255, which is right there, right? And at the SN2 position, it's going to cleave right here at the cholesterol backbone. So what we have is two released fatty acids. There's nothing unique about them. So we don't know, are they SN1 versus SN2? However, with EAD, we're going to fragment right here. And it actually makes unique fragments. For the SN1, it actually captures one of the carbons from the glycerol backbone. And the SN2, it actually splitting the ester itself. So as a consequence, we actually can generate a series of diagnostic fragments. So this series of numbers right here refers to the CID-based fragments that we're also going to get in an EAD experiment. So that's the individual fatty acids being kicked off. But then we have the unique fragments, SN1 here, which is going to fragment to contain that additional methylene group from the glycerol backbone, and the SN2 here. So now we have a series of diagnostic fragments to allow us to identify SN1 versus SN2. And also note, we have diagnostic fragments for plasmalogens, for alkyl ethers, and also for the sphingoid backbone. I think this is pretty amazing because Bob Murphy has spent years trying to figure out a unique way to identify plasmalogens from alkyl ethers, from odd chain acyl linked. And really in mass spec there wasn't an easy way, but with EAD we get a very clear fragment. And you might say, well, look, there's a 311, 331 right here, and then there's a 311 over here, but look at the mass there. That's certainly a significant enough difference in mass that we can distinguish those using accurate mass. With a nominal mass instrument, no, but you can with accurate mass instrument. And finally, the double bond position. Some of you may have tried this in the past. It's kind of popular in the 2000s where you would add lithium hydroxide or some sort of lithium salt to your sample. You would lock the charge at the carboxylic acid, and then you'd get site-distance fragmentation. So essentially, you would start nibbling away at the alkyl chain. And you'd say, in this case, you can cleave here, here, and when you cleaving here would give us a mass difference of 14, 14, but as soon as you get to the double bond, you're going to have a different mass breakage. And I can show it a little bit better with the cartoon here. This is a typical spectrum, EAD spectrum for PC. So those of you who've done PC analysis in the positive ion mode, what you normally get is just a gigantic peak at 184, a little bit of the precursor ion, and maybe some lyso information. Here we have almost 400 peaks. And I am here to tell you, each one of those has structural information that's relevant to the structure of that molecule. What we found is that in this region right here, we get information about the regioisomerism, where are the fatty acids attached to the glycerol backbone. And this region here gives us information about the alkyl chains. As you can see, basically we're nibbling away. This is our intact molecule. Here's minus the terminal methyl group, so the difference would be 15, and the mass difference 14, 14, 14, 14. And when you get to a double bond, the mass change might be 12. All right, so all you do is then just nibble away. Here's our structure of our molecule, and you just count down the peaks until you see a mass difference that's not 14, and you know the location of your double bond. All right, and it turns out this works really well on a LC time frame. I'll be honest, when we start getting 4 and 5 double bonds, it gets confusing. So I would imagine that we need a better software to make that happen on a routine basis. But manually, you can certainly find the positions of 1, 2, 3, and 4 double bonds fairly easily. So one of the another cool thing about electron-based fragmentation is that it's actually a mixture of radical and non-radical fragmentation. Homolytic scission is radical fragmentation, where you split the molecule and one electron goes to the non-charged particle and the other one goes to the charged fragment. Or we have non-radical, which would be heterolytic scission, which is the transfer of a proton, right? And in electron-based fragmentation, it favors radical or homolytic scission. However, it turns out that there is a difference between that ratio. You're going to be preferred homolytic scission versus heterolytic scission based on the nature of the double bond. So in this case, for a cis double bond, it turns out that cis double bonds prefer homolytic scission, or they undergo homolytic scission more readily than heterolytic scission. By contrast, trans double bonds prefer to undergo heterolytic scission. So it turns out you can actually look at the, just simply from the MSMS spectrum, you can see a propensity. It's not cut and clear. It's not like it absolutely is heterolytic versus homolytic, but you can actually see that there's a, if you run this at several different kinetic energy value ranges, you can see a trend where one is going to be more towards homolytic versus heterolytic scission. So you can actually determine this. This is the only part that I would say is not really effectively done on the LC time frame. You can get the data, but if you decide you have a biomarker that you want and you want to determine absolutely is that a cis or trans double bond, you might have to do additional injections where you're going to ramp the kinetic energy of those electrons, and you should be able to do that experiment and be able to determine cis or trans. So let's bring it together in an example. This happens to be 16018.1 PC. Just to point out, this was actually done with NIST 1950 plasma. This was a discovery experiment. So this was on an LC time frame. And we got this data. Based on the precursor mass, we know that it's going to be PC34.1, or at least that made sense, but let's use the proof from the EAD spectrum to prove it. So we have our 184, like, absolutely, it's a PC, but it could be sphingomyelin, all right? And we know it's not sphingomyelin because we have our doublet, the 224, 226 down here. We know based on the this region right here, we can find a diagnostic peak for the SN1 position. So we know that the SN1 is 16.0. By default, 18.1 has to be at the 2 position, although there is an SN2 fragment there. Then we have, we can isolate our double bond location. In this particular case, we're able to determine cis versus trans. So essentially, this is complete structural characterization of a lipid on an LC time frame in a discovery experiment, all right? This had to be done manually. That's the unfortunate part, all right? So how do you approach this? We do, one thing I will say is that Hiroshi Sagawa, the guy who's at Riken University who created, you guys know, worked very closely with them for MS Dial. They've uploaded a number, I'm not sure exactly the number. I heard it was 8,000 or 9,000 structures or EAD spectra, in silico generated EAD spectra for lipids. So right now, that's the one program that we recommend at SCIEX. We don't have an internal solution for this automatically. We're working with Hiroshi to make it work with MS Dial. There we go. And you can also do complicated molecules. PC is pretty straightforward, but this is an incredible picture of basically GM3. This is a ganglioside. And Takashi, the guy who invented the EAD cell, was very proud of himself when he showed me this. He's like, I figured out every single one of these peaks are. He was able to identify the fragmentation of this. And how would he do that? Well, you can take your mole file, right? And you put it into, you can associate that mole file, we call it fragment pane, and you associate the mole file with your MSMS spectrum, and it'll actually generate in silico fragments, and then it will match them up. This, we're looking at the monosodiated, this is the disodiated. Either way it works, but we find the monosodiated seems to be more intense in terms of peak intensity. So I don't think it comes as a surprise. Most of you guys assume when you're thinking about accurate mass, it's an amazing discovery tool. But I think one thing that we're realizing, because of the speed of that detector and because of the dynamic range and the sensitivity of the mass spec because of the xenotrap, it also could be used as a quant box. And so wanted to actually do this experiment with steroids. We did a series of experiments where we were trying to determine, could we measure plasma steroid analysis, and this happens to be in the NIST 1950. So what you're looking at here is the TOF-MS, and clearly, even with a narrow XIC window, there's a lot of interference. But when you go to the what we call MRM-HR or high resolution MRM, where you take your precursor mass and a narrowly excised XIC window, we're actually able to get a very nice chromatogram of all 18 of the steroids that we measured. And in fact, when we calculated the LOD and the LOQ for these series of steroids, we found that the concentration that we found in the NIST 1950 was within that limit of quantitation. So as a result, we can do quantitative performance that's similar to a high-end triple quad. All right, and this was with 60 microliters of plasma. But there's something interesting about this assay. I mean, it took 17 minutes to do the assay, right? And the reason for it is this. You'll notice these bands. Basically, this is just showing you the name, the formula, the mass, Q1, Q3, basically all the parameters. But if you look at, there's some that have the same color, like the 11-deoxycorticosterone, 17-hydroxyprogesterone, they're the same colors. Why? Because they're isomers. And it turns out these two have exactly the same Q1 and Q3 fragments, all right? So the only way to be confident that you have 11-deoxycorticosterone versus 17-hydroxyprogesterone is to have good chromatography, right? To have a standard, to say this is its retention time, we have to have some orthogonal means by which to identify this molecule. And it turns out that's not the only pair. The ones in green, blue, red, they're all molecules that are isomeric pairs. And so as a consequence, we have a long method to be able to make sure that we have assurance they're separated. But what about using EAD? What if instead of doing a CID MRM transition, what if we switched over to electron-based fragmentation? Now, the one downside to that is it is not as sensitive as CID-based fragmentation, but we can turn it on and off at will. I could have a list of 100 MRMs and only turn on EAD for one of them. And why would I want to do that? Because maybe I can get something out of EAD, specificity, that makes it worth my while. So here's looking at 11-deoxycorticosterone versus 17-hydroxyprogesterone. And you can see with the CID spectra, they're identical. So again, chromatographic resolution is our only hope in that regard. But turns out with EAD, we have 3 fragments that are absolutely unique to 11-deoxycorticosterone, and we have 2 fragments that are unique to 17-hydroxyprogesterone. So what you can do is, instead of having to have chromatography resolve those guys, why don't we take our 17-minute run and squeeze it into a 10-minute run? That's a lot of time difference. That's basically doubling your capacity to run a steroid analysis. And what we're doing is assuring our specificity with EAD rather than chromatography. So overall, that's something that we're actually in the process of proving that proof point, being able to show that using EAD we can make a shorter run. But we're also capitalizing on this with acyl carnitines, lipid mediators, as well as bile acids. So I want to show you some new data that's hot off the press about bile acid analysis. We got a kit from Cambridge Isotopes. Basically, they have 18 bile acids and their deuterated counterparts. And I wanted to see, test the sensitivity of the assay, but also really test the dynamic range of the instrument. So we're going from 10 picograms to 10 picograms per mil to 1,000 nanograms per mil. Straightforward C18-based chromatography. This was a chromatographic strategy designed by Dr. Thomas Horvath at Texas Children's Hospital in Houston. And this is kind of an example of what you're looking at. This is at the TOF-MS level. And this is really a good example as to why bile acid analysis has been challenging, is because we're looking at bile acids in the negative ion mode. And for any of you who've done mass spec in the negative ion mode, that area between 200 and 500 is full of a bunch of crap, all right? All the solvents, the contaminants in most people's solvents are going to be fatty acids. They're going to be in that mass range. And you can see the really high background. This is with standards, and we have a huge amount of background associated with at these masses for our molecules of interest. So obviously TOF-MS is not going to be sufficient to give us the sensitivity we want, so we wanted to move over to TOF-MS-MS or MRM-HR. And here we can see really nice resolution and separation of all the different bile acids. In particular, I point out chenodeoxycholic acid and deoxycholic acid. They are very, very close to being on top of each other. And unfortunately, they are isomers in terms of mass spectrometry. All right. So we need to have this 15 to 20 minute run to be able to resolve those sufficiently. All right, so the same kind of idea. One thing though is we're getting from anywhere from 100 picograms per mil to 1,000 nanograms per mil linear dynamic range. So it's definitely a quantitative, has a lot of quantitative power in this assay. And this is something that kind of blows my mind. The 7500 Q-trap, or the 7500 instrument, is arguably the most sensitive commercial mass spectrometer available. And in particular, this is in the negative ion mode, and it really sings in the negative ion mode. So these levels right here, this is the LOQ determined on the 7500 by Thomas Horvath. And notice we're at like 20 nanomolar. Maybe we get down to the picomolar. Look what we can do with the 7600. You're like, how is it possible we could beat a triple quad by 2 orders of magnitude in sensitivity? It turns out to do with the narrow XIC window. All right, we actually can extract, rather than doing an MRM, which is basically unit resolution between Q1 and Q3, right? Here we're going to excise a very narrow fragment mass, plus or minus 5 millidalton. And in doing so, we're able to get rid of all the noise, right? So by reducing the background noise, we've improved our signal to noise. So all the ones in green, we're beating them by over 1 to 2 orders of magnitude in sensitivity on the triple top. If they're yellow, they're roughly the same, and if they're red, there's only one compound that gets beaten by the 7500. I think that's kind of amazing. So, you know, the cool thing about this instrument is that, yeah, you can do discovery, you can do some very cool qualitative analysis with it, but at the end of the day, if you need to use the instrument for a quant assay, you can, and you might be able to actually do your quant assay faster on this instrument because of EAD and then the narrow XIC windows. So last little bit, remember I mentioned cheno-deoxycholic acid and deoxycholic acid, how they're very closely, almost on top of each other. Here's the only difference, the hydroxyl is here versus here for these two molecules. They have the same Q1 and Q3 transitions in nominal mass, but turns out we can find a unique fragment in EAD. Here's the CID spectrum of deoxycholic acid. This is the fragment pane I was telling you about, so you drop in the mole file, you relate it to your MSMS spectrum, and you can actually identify the fragments. EAD clearly has a huge number of fragments, and in particular, pay attention to these guys right here, because those seem to be unique to DCA. And we're able to find, using the fragment finder, a fragment here, one of which is 255, and again, I mentioned this series of fragments right here appear to be unique to DCA, and indeed they are. This is taking the MSMS spectrum DCA and overlaying it on CDCA, inverting it, and you can see that we actually had 4 fragments that were unique to DCA that are not in the Cheno DCA. And so if I do an XIC of DCA standard, I get a nice peak right here. The same sample, so it was a mixture of DCA and CDCA. I did the same XIC window and I saw nothing. So here we found a unique MRM transition for DCA. I no longer have to worry about trying to resolve those two peaks. All right. So again, the trade-off is sensitivity, just like you can imagine in mass spec, sensitivity versus specificity. So when you need it, you can turn it on. When you don't, you keep it off. And with that, I hope I was able to give you an overview. I thank you very much for your time, and I'd be happy to answer any questions you may have.
Yay. Great presentation. I'm glad we recorded it, so we can post it. Also, I can give it to my future qualifying exam candidates in chemistry who sometimes don't know when we do our practices, and then you know, we have funny surprises. So that might be good for our future candidates. So are there questions? Oh my gosh!
All right. Love it.
Maya first.
Yeah, hi, great talk. Great talk, thank you.
Thank you.
I was wondering about the library, the in silico library that you mentioned by Hiroshi. I wasn't quite clear. Is that already usable, or is that still a work in progress?
It's in version 5.2, so I don't think it's usable. It's not freely available now. They're doing the beta testing essentially in-house, but it's in version 5.2.6 or something like that. So it's going to be available, freely available very soon, but apparently it's not available online yet.
Okay.
Yeah.
Thank you.
So they're still working on it, but it's very soon it's going to happen.
Okay.
Following that thought, since all the fragments specific to the stereoisomers will be lower abundant compared to the very dominant fragments,
Yeah.
how would it affect the scoring system to count for that really low abundance?
Right. I mean, you guys are familiar. You guys do a lot of accurate mass work here. You know, even a very small peak in a time of flight instrument, it can be a real peak, right? It's your background is much lower on a time of flight instrument than it would be, say, on a triple quad, where you want to have like e to the 4, e to the 5 signal before you say, yeah, that's my molecule. Honestly, it's compound dependent. Clearly, it's going to be less sensitive in the EAD mode than CID mode. So that's the because it's just not an efficient reaction. If turns out if you do an EAD reaction of a molecule, about 70% of the precursor is still around at the end of that reaction. So it's clearly not going to be as sensitive. I don't know if I'm getting to where you're going, but you know, if you have a peak that's 10, 15 counts per second, that's a real peak. You can, you know, certainly do qualitative work. We're still trying to suss out what is the effect on LOQ and LOD, and I don't have the answer to you on that, but it's clearly going to be lower.
Yeah,
Or
I
higher.
understand the low sensitivity.
Okay.
That's the challenge for EAD and other
Yeah.
orthogonal fragmentation for that too. So I'm just thinking if anyone is annotating, is going to use our naked eyes to do that without zooming into 100. So what would
Right.
be a good way is the scoring to put a good enough weighting to say now let's match the low abundant
Yeah.
fragments too.
So the only scoring really that we have access that I've played around with, and I think I have it here, is on that fragment pane where we actually are looking at theoretical in silico fragments versus what's actually in our mass spectrum, and you have the ability to raise and lower that threshold for the scoring. At this point, I would say we're not quite there yet to be able to say definitively, yeah, this is the way you do it. We're working on we have probably a better sense with metabolomics, but with lipidomics, we're not quite there yet, and able to say what is the threshold that we need to have in order to be confident for our scoring parameters. But you know, if like I said, if you have a peak that's, yes, you have to zoom in, all right. But as long as your threshold is below that, you know, that level of like 10, 15 counts per second, those peaks can be real. I mean, automated is the challenge right now, and I don't know the answer to your question in terms of how would we automate that and generate a quality statement about that data. So I'm not sure.
Yeah, so I am always interested in compound identification.
Mm-hmm.
I wonder how well like EAD spectra is picked up by like the community that are working on in silico fragmentation tools to learn and adopt to that, because it's like
Yeah.
always CID based. So like how well
Yeah,
is that picked up now?
And I'm blanking at his name. Maybe Lauren, you remember it. The fellow in he spoke at ASMS for us for lipidomics. He's from Europe.
Justin van der Hooft?
No, there's another shoot. Well, he's designing some software that does the SMILES based structural relation to in silico EAD fragmentation. So I'll remember his name. I apologize, but he's doing. Now it's going to bug me.
Tucker?
Pardon?
Tucker?
No, gosh, it's killing me. I will remember. But he's done some really nice work, and he presented on our behalf. I should be a little bit more aware of his name, but he is making tools for de novo structural analysis of EAD-based spectra. So, and it's based on the SMILES structural. All of his algorithms use SMILES to construct the molecules, and then he's got algorithms that are going to relate the fragmentation pattern to the structure of the molecule. That's the only thing I know about that's going on yet. I mean, it's still really new.
Yeah, it's like I feel like last ASMS it's been picking up.
Yeah.
So I just wondered within the last 2 years if it's, you know.
Zamboni,
picking up.
that's his name. Zamboni.
Oh,
Yeah. Sorry.
Oh,
Yeah.
oh,
Yeah.
okay. Uli?
Yeah, can I ask 2 questions?
You can ask 5.
But I guess-
Only
So,
2.
What? One is was about you said that the benefit of the xeno trapping is mass dependent. So mostly because usually we bias the center. So
Right,
now,
right.
now we benefit more in the end than in the beginning, not so much in the center.
Well, it's all equal now.
Or all equal.
It's
yeah,
all equal
right.
now, yeah.
So, but the benefit over what we have now is going to be not equal now.
Yeah, you'll see a bigger benefit for, say, metabolomics, lipidomics at the low end. Correct.
Right, and then now we have all the fragments. So does this affect the fermentation pattern that we see? That we will finally see differences.
I think the intensities will be different. Yes.
Okay, so
Yeah.
for the same 30 EV that we have with the triple top, we're not going to get exactly the same mass.
The ion ratios will definitely be different.
Got it.
Yeah.
Okay, so that was one question.
Yeah, no, that's a really good question too. That kind of screws people up, doesn't it?
Yeah. The other, well, maybe not if they use, depending on what similarity approach they go for, right? Another question is, you mentioned even that maybe at some point it will be kind of similar with EIMS, which I'm not sure because this electron bombardment of or electron impact of an ion is not the same as electron impact of a neutron, but since you are generating so many ions now, and and it is very it does resemble EIMS, right?
Yeah.
So will at some point SCIEX just make a single quad LCMS because with GCMS we ask ourselves the question all the time: do we really need the high mass accuracy and high resolution?
Yeah.
Where sometimes it's beneficial for a lot of the things that you showed, but in a lot of industries not so much, and they say single quad is fine.
Yeah.
Because we have so many.
They just need a detector. I mean, they don't really need a mass analyzer.
Do you think LC EAD single quad is in the
Or tough.
or a tough? If we
I wouldn't go for single quad because of the speed. But
I can tell you that it's not on our roadmap, but I don't know how long we're going to be able to say we're the only ones with EAD. I would say it's probably not very long. I would imagine some.
What about Agilent?
Yeah, exactly. That's right up Agilent's.
No, you can't
alley.
purchase it.
Pardon?
It's there.
Not with kinetic energies that high.
Oh, okay.
Yeah.
Well, then I don't know.
Yeah,
I don't know what
yeah.
exactly, but they do have acquired that company and they offer it now.
Yeah. So, not sure. It's good. I know that as far as I know, in the roadmap is to make current instrument bigger and better. I doubt they're going to scale down. That's usually not SCIEX's way. Yeah.
So I see several more people. Shen first, and then what you? First Shen.
I have two questions too. Oh, very different. When we tested the Xenotop, in the same peak, in the early and late, because the later data point has a more reaction time, the MSMS looked slightly different, but I don't remember how drastic different to make the annotation different. So there might still be a case.
So, I'm not really sure in your specific example on there. One thing I do know is one of the challenges that they face when they're designing this instrument is to try and minimize secondary fragments, because that really confuses the situation. If you take a fragment and then make a fragment of a fragment, that really is not very helpful in understanding the original structure. So the reason why we still have 70% of our precursor ion left after reaction is because they designed it so that about 90 to 95% of the fragments are all primary fragments. So what's more important, I think, is not necessarily that ion ratio, but it's what fragments are being generated. And at the, I think the default value is like 3,500 milliamps, and that's basically the current of the electrons, about 13 electron volts and 30 milliseconds. Yeah, the vast majority of those fragments are going to be primary fragments. And their ratios, that's something I'm not sure about. But I will say that they are primary, and if we were to elevate it too high, and that's one thing that's going to be a problem with negative ion mode when we go to 70, 80 electron volts, are we starting to create secondary and tertiary fragments that are going to confound our ability to interpret the spectrum or identify. But I would say right now, the only thing that's going to affect your specific example that you mentioned is probably the ion ratios, not the actual fragments themselves.
And to the direction to application.
Yeah.
All the EAD application, maybe collaboration with someone. Have you seen when that special elucidation of structure actually show differential changes in cohort and stuff like that?
Oh, yeah. That was a question I got yesterday at Stanford. And the answer is no, not yet, just because we haven't done large cohorts with that. We
like small, like in a phenotype, in a
right. That at this point we just really haven't gotten to that. I mean, we are engaged with a number of people now. I intend to engage with you guys in a much stronger collaboration, and that might be a great experiment for us to do together.
Yeah, there's also like grant call just to validate like preclinical biomarker from previously Alzheimer's P38, and now we're saying not we can do it.
Yeah.
There's grant.
I think that would be that's a necessary set of experiments that would be really great to maybe engage with you guys, because I think you guys have the data capability to really look into that in a very unique way. So it's exciting to think about. And I guess we're going to talk about that afterwards. So.
What you?
Yeah. Very interesting talk. So I have a question first for the Xenotop 7600. So my question is, you have the ion trap to make sure you don't bias the ions by mass.
Mm-hmm.
Do you also use this like method to deal with MS1, or it's only applied to MS2?
It's only applied to MS2, and the reason for that is we blow apart our detector. I mean, it really, yeah, so we're using the power of Q1 isolation to limit the number of ions that are actually going to hit our detector, right? So with MS, we do not use the xenotrap. The xenotrapping is off when we're doing MS, just because of the fact that we would really overwhelm our detector.
Okay. So,
Yeah.
So what type of detector is used in Xenotop?
I think I showed a picture of it. See if I can show. I need my glasses. I don't know the exact specifics of it, but I can. It has the details.
Oh,
It's a
There we go.
style glass plate with
SCP or
what's that?
it's a multi-channel.
Multi-channel plate. Yeah, I think we use 4 landing zones.
It is four. Yeah, it's a 4-channel plate.
Yeah, I mean it physically had up to 8, but I think we used the center 4, and this design in the 66 is similar to the 66 in that it went from a simple kind of binary type of readback to a graded readback where I think up to about 4 ion strikes per bin it's giving additional signal readback, so you get a little bit more dynamics out of that. So,
Yeah.
so it's a timed, I think we call it a timed analog to digital conversion. So it's a little bit different than just a pure, kind of the previous TDC design was a little bit limited in that use. So.
Okay, thank you.
Yeah, he knows much more than I do about it, so I can't add anything to that.
For the MS1 data acquisition, is there a pulse time that people can join to focus on a certain mass range?
So, Lauren was talking about the bins. So essentially, as you go further up in molecular weight, you tend to increase the number of bins to sum up to call it a point. So there are ways you can tweak the detector that will accommodate higher mass ranges, but I don't know if that's the question you're asking.
Oh, I mean the pulse time basically is the time you allow the ion to go after the second particle, because you want to, like, if you leave longer time, then the larger mass ions will be
Gotcha.
tossed into the
Yeah.
off and.
That's a question I don't know. Do you have any idea about
I'm
that?
not sure I understand the question. So.
Oh yeah, I think that is a design with the broker top. Basically, if you want to focus on the C1 tablets with a mass with a lower mass having compared to lipid, and then you set the pulse time to maybe 3
we have-
microseconds.
Yeah,
Okay, I think I
okay.
know the answer.
Yeah.
So,
Go ahead.
a lot of Brooker's technology has to do with duty cycle enhancement via the mobility cell itself, right? So that's similar in concept to what we're doing with the Xeno technique, although we're not using mobility to do that. We're just using very careful beam handling and essentially conversion of a continuous beam of ions into packets of ions that are then very exquisitely passed into the accelerator. You have to think about the time frame of the TOF accelerator and pulsar electronics. We're talking microseconds of time per TOF pulse, and then when you see a spectrum, it's typically the summation of tens to hundreds or even thousands of TOF pulses, and in that time frame, at the timing of the detector, I mean, the detector's way faster than any sort of acquisition time level thing.
Yeah.
But I would look at all of the vendors have done a lot in the last 10 years. I would say that we were later we were a little late, but we've really caught up in terms of beam utilization, and that would be Thermo's C-trapping, Brooker's passive technology, and now Xeno. They're all
Yeah.
using much more of the beam.
So on the 6600 that you guys have here, you have enhanced mode. I don't know if you've ever used that. I know you're the 66 runner, but there's a mode called enhance. And it means, you know, remember that bias, I was saying, that Gaussian bias? With the enhanced mode, you can shift that Gaussian distribution around. So that would be to your answer for, you could change the enhanced mode to accommodate larger molecules, but the Xenotrap takes care of that, by the way it's working.
Yeah, when we were designing the instrument and then asking the question, what were we going to bring to market? The first thing that they asked us was, do you want, you know, would you want more resolution? Would you want more sensitivity and even electron fragmentation? And we thought about it. And we're like, you know, I think resolution, chasing Thermo and their game of more resolution versus doing something that played more to SCIEX's core strengths of sensitivity, quantitation. That really made sense to us to go the direction of sensitivity and quantitation. And I thought, you know, an EAD, that'd be really cool too. But I said, I think we could wait on EAD if we could get the sensitivity faster. And at the time, we didn't realize that what the question that R&D was asking us was really the question between xenopulsing and the concept of having 2 ion traps in the ion path versus just the one, which Paul mentions was the enhanced mode only ion trap. By getting 2 ion traps, the EAD cell and the Xeno gate at the back, we actually were able to get these gains without the mass bias, and that was a really critical thing. But we had to have those 2 features, the sensitivity from xenopulsing and EAD, were one technology effectively, and had to be brought to market at the same time. So it was an interesting story of how that evolved, but I think it really plays to our strengths and to what our users expect from SCIEX. So.
Other questions?
So actually, I have one final question about resolution. So you mentioned the resolution for Xenotop can be about 30,000.
35 to 45,000.
Yeah, so
Depending on the mass size.
that is much higher than other top SPAC. So how Xenotop did it?
I mean, it may be, I'm not sure how they do it, to be honest with you. I mean, it's the N wave, so the resolution is going to be dependent on the path length, right? So since it's an N wave, we're effectively getting an additional path length of that top chamber to be able to get that resolution.
The biggest innovations came with the X500 actually, which was the little brother of this instrument.
Oh, sorry, the little one?
X500.
The X500 is kind of the little brother, because the 6600, which you guys are familiar with, has 3 high voltage supplies in the top region. It's extremely costly, and each of those supplies has a certain amount of drift, voltage drift and output drift. And so that affects mass accuracy and robustness and, you know, how often it needs to have parts replaced and all sorts of things, cost. And when they came up with the X500, they literally stripped it down to the bare minimum. I think we really only have 2 supplies, one for the liner and one for the accelerator. I think we had 5 on the 6600 in total. And so by doing that, we actually were able to drop the amount of potential. We went from 15 kilovolt push to 4. We went from a push-pull to a push only in the accelerator. So there were several design innovations that came with that exist in the 7600 that actually have decreased the cost and increased or maintained or slightly improved the resolving power over the 6600. So it's a really exquisite design. I mean, the people that worked on it, Takashi and Hoffler up in Toronto, they did an amazing job, and it's far more rugged than a 6600 because of that.
All right. Thank you so much. Any final questions? No? All right. Thank you so much again for a great presentation and good discussion.